welcome again to Chemistry 101. It's your instructor, Dr. Ismail Badran from Qatar University, and today we are going actually to start Chapter 2 in this course. So I hope that everybody is doing fine during this pandemic period, and you had a chance also to solve some of the problems and exercises and the online assessments related to Chapter 1. So okay, let's start. Okay, so Chapter 2 is actually, here we start with real chemistry, and we're going to talk about atoms, molecules, and ions. Not every section in this chapter is actually required, so as I said last time, some sections are omitted. Section 2.1 and 2.2 are omitted. It's a home read, so we're going to start with section 2.3. Also, section 2.8 in this chapter is omitted from the book, so we're going to only cover 2.3 all the way up to 2.7. These are the learning outcomes that you will learn by the end of this chapter. You can go over them. Before we start, I invite you to watch this YouTube video just to motivate you into the topic and refresh your mind on the idea of atoms, molecules, protons, and neutrons, and all of that. There's also a website called fit.com. This is a nice website. It's a very nice interactive learning tool that you can use to practice some of the concepts and grasp some of the concepts related to chemistry. So this is a specific fit simulation for chemistry for this chapter. Please take this link into your browser. Enjoy watching the presentation as well. Okay, so we start with atomic number, mass number, and isotopes. So everybody knows that an atom is composed of protons, neutrons, and electrons. So we define the atomic number, which is Z, to be the number of protons in the nucleus. Okay, so and the mass number A, it's the number of protons and the number of neutrons. So in this case, A would be equal to Z plus the number of neutrons. Now, protons and neutrons are actually called nucleons because they are inside the nucleus. Okay, so let's take an example. That would be hydrogen. Hydrogen has an atomic number of 1 and a mass number of 1. So atomic number of 1, that means it has only one proton and one electron. And if you want to figure out the number of neutrons, that would be 1 minus 1, that's 0. So there are no neutrons in the hydrogen atoms. But we have something called isotopes. And isotopes are the atoms of the same element, X, with different numbers of neutrons in the model. So if you know, I don't know if you know this, but there are other isotopes for hydrogen. One of them is deuterium. Deuterium has an atomic number of 1, same as hydrogen, and a mass number of 2. And therefore it has 1 electron, 1 proton, but it has also an extra neutron on it. And there is also another isotope for hydrogen, it's called tritium. And tritium has a mass number of 3, and therefore it has actually 2 neutrons inside that nucleus. One more example is uranium. You know, uranium is widely used in nuclear reactors, and you might see this common image for a nuclear reactor. Nuclear energy is used to, of course, produce electricity in many parts of the world. And uranium, which is the element that is used in these nuclear reactors, there are commonly 2 main isotopes for uranium. Uranium has an atomic number of 92, so and it has 2 isotopes. Well, it has many isotopes, but the famous 2 is 235 and 238. So uranium, they're both having an atomic number of 92. It's impossible to have a 91 or 93 because if it does, that would be another element. So the atomic number does not change between isotopes. But the uranium-235, if you do the math, well, from the atomic number you can tell that there are 92 electrons on it, 92 protons. If you subtract 235 minus 92, that would give you 143 neutrons for the first isotope to the left. The other isotope, which is the uranium-238, if you do some math, you subtract Z minus A, that 238 minus 92, that would be 146 neutrons. So the only difference between the two is the number of neutrons that they exist between these 2 isotopes. Now I want to leave you with a little homework here. Is uranium actually is used widely in nuclear reactors, and it's one of them that is active, is the one that is, we say, radioactive. Okay? So I want to, and there's some, we can enrich uranium by converting one isotope to another. So when I ask you a question, and you can research the internet about that, what does uranium enriching means? And what is which one of these isotopes is actually the one that is used in nuclear atoms? So you can research this yourself and get me the answers next time. We have a question here to practice the counting of neutrons and protons and electrons. It says give the number of protons, neutrons, and electrons in each of the following species. So we have A, sodium 2011 and sodium 2211. We have also oxygen, we have carbon 14. So I brought this into I want to organize my solution to this problem through a table here. I wrote what is required in the question: Na2011, Na2211, O17, and C14. Let's take the first one. So Na2011, I know the atomic number is 11, the atomic mass is 20. It does not matter which one actually in the top and bottom. The convention here, the common convention is to put the atomic mass in the top. But in rare cases, you might see this is written another way. This is written like in, let's say, sodium. I see some books writing it this way. I see some books writing it this way. So it does not matter for you which one at the top and which one at the bottom. The bigger number, the higher number is always the atomic mass, and the small number is the atomic number, okay? Anyhow, let's clean this again. Go back to our subject. So sodium 1120, that means I have 11 electrons for sure. I have 11 protons, because in a neutral atom, not an ion, the number of protons should equal to the number of electrons. And you see me here referring to electron by E minus because of the negative charge of electron, and a proton is a positive, so it's a P plus. The question is, how many neutrons do we have? You can tell how many neutrons you have easily by subtracting the two numbers from each other. So 20 minus 11 is 9. So we have 9 neutrons in sodium atom. Now we have another sodium atom, but it says 1122. Now what is this? Which one is correct? Well, both they are correct because they are both isotopes of sodium. Okay, they are both isotopes of sodium, and we're going to talk about the average mass soon in chapter 3. But again, the number of electrons in this sodium will be 11, and the number of protons is 11. So the number of electrons does not change for the same element. If we're talking about sodium, there are always 11 electrons on it. If there are 12 electrons, that wouldn't be sodium, that would be something else. If you subtract the Z minus A, these numbers, so 22 minus 11, that would be 11. So 11 neutrons in this sodium isotope. Oxygen 17, he's not telling you actually what is the atomic number, so that's maybe a good chance to look at the periodic table. And for this course, for chemistry, I advise you to have a copy of the periodic table handy in your computer or a printed copy. Just by looking at the periodic table, you can tell that oxygen has actually atomic number of 8. So this is something you might need to figure out by yourself. But we are talking about the 17 oxygen, okay? Oxygen is actually the one that we know is 16. Oxygen 16 is the atomic mass. But here we have an isotope of oxygen that has an atomic mass of 17. And we're asked to count the number of protons and electrons and neutrons. From the atomic number, you can tell right away that this should has 8 protons, 8 electrons. You can subtract 17 minus 8. That would be 9. So 9 neutrons. And finally, C14. So C14. When you say C14, that's the atomic mass. You check the periodic table, you will see that carbon has an atomic number of 6, and therefore there are 6 electrons, 6 protons, and 14 neutrons. No, that's wrong. That's a mistake that people do all the time. They think the atomic mass is equal to the number of neutrons. The number of neutrons would equal to the 14 minus 6, because remember, this 14 represents the number of neutrons and protons in the nucleus. That's the atomic mass, okay? So 14 minus 6, that would be 8. So 8 neutrons in the carbon atom, in the carbon isotope of 14. So that would be the solution for this problem. Now, moving on. So now we need to talk about the periodic table. The periodic table, and you might cover this in school, is a chart in which elements having similar chemical and physical properties are grouped together. So we group the groups that they look to each other in one group. And also in the modern periodic table, the elements are arranged by atomic number. In the historical, the old one, we've been the scientists were arranging it by mass number, but now it's more correct to say that it is arranged by atomic number. There are three main categories of elements in the periodic table: metals, nonmetals, and metalloids. The metals are those elements to the left side of the periodic table. Usually they are good conductors of heat, electricity. Examples are iron, copper, magnesium, sodium, all of that. Nonmetals are those to the right side of the periodic table, and they are usually poor conductors of heat and electricity. We have also some metalloids in the middle, that they have kind of shared properties between the two. This is a picture of the modern periodic table that everybody saw before. Starts with hydrogens and helium, and all the elements are there. And as we go here with advancement in technologies and science, we are actually discovering more elements. I think we are now up to 120 or 120 something. And these elements, some of them, they are known a long time in history, like carbon, for example, or iron, or oxygen. But some of them are new. We just knew them in recent years. The column in the periodic table is called the group. So the vertical column is a group, is called the group, and the row in the periodic table, the horizontal row, it's called the period. So we have 7 periods in the periodic table if you count them: 1, 2, 3, 4, 6, 7. It's not 9 because these in the bottom here, the lanthanides and actinides, they're actually embedded into the periodic table here. So we have only 7 periods in the periodic table. We have also many groups. We have 8 main groups. We have some transition metals. The first group is called 1A. The second group is called 2A. And then we jump here, say 3A, 4A, 5A, 6A, and so on. Okay? You can call this, the transition metals in the middle, 3B, 4B, 5B, and etc. There are 2 different ways of naming these groups. Another system is called them 1, 2, 3, 4, 5, 6. But in this course, we're using 1A, 2A, 3A to represent the main groups, which is the first 2 groups and these 6 groups to the right. The middle groups here, we call them B. These are the transition metals. Okay. Some groups, they have special names. For example, group 1, it's called alkali metals. Alkali. That's an Arabic word, alkali, because most of the chemistry, or big part of the chemistry, has been studied or has been developed by Arab scientists, and therefore you can find many Arabic terms in chemistry. Chemistry itself is an Arabic word, al-khimia, which means chemistry. So alkali metals is group 1. But hydrogen is not one of them. We don't count hydrogen is to be in the alkali metals. So there are lithium, sodium, potassium, and other ones. Group 2 is called alkaline earth metals. Alkaline, some books or some resources, they name them alkali earth metals. I would say that they are alkaline earth metals. That's a more correct way to name them. Alkaline earth metals. So the alkali metals is group 1, alkaline earth metals is group 2. We have also halogens, which are the fluorine, chlorine, bromine, and iodine halogens. And we have also noble gases. Sometimes they call them rare gases or noble gases. These are group 8, which are basically do not form compounds, generally speaking. Some of them, they actually do. Actually, the other groups, they do have names. For example, this group with oxygen, sulfur, and beryllium, it has also a name, chalcogenides it's called. There's carbon group. So you can find in literature some names for these groups, but in this course we are just focusing on these groups in red, okay? The 4 groups: alkali metals, alkaline earth metals, halogens, and noble gases. And for the periods, they have no names. We just call them period 1, which is hydrogen and helium. Period 2, which is lithium, beryllium, and so on. And then 3, 4, 5, 6. We call the periods by their numbers. In the middle, we have the transition metals, which are group 3b, 4b, and so on. I forget to say that everything in green in the periodic table in front of you is metals. Okay, everything in green is metal. So the metals are not only group 1 and 2, and that's a misconception for many chemistry students. The metals contain group 1 and 2, and all the transition metals, everything in B here, and also some actually metals that they are appearing here. So, for example, although carbon is a non-metal, but don't think everything in its group is actually non-metal. No, in the carbon group we have a non-metal here, but Pp, which is lead, is actually a metal. Same thing for nitrogen. Nitrogen is non-metal. It's in blue, but bismuth, for example, Bi is a metal. So everything in green is metals. Everything in blue is non-metals, and we have also some metalloids, which are colored by purple here. Pink. Okay, so that's enough talking about the periodic table. This is a multiple choice question, just to check your understanding. Which of the following is not a common name of a group of elements in the periodic table? We have been given five choices: alkali metals, transition metals, halogens, noble gases, alkaline earth metals. So which one of these is not actually a name for a group in the periodic table? You can think about this and come up with an answer later. Enough talking about elements. So the periodic table is composed of elements, but most elements, they don't actually exist by themselves because they are very reactive. So for example, sodium, it does exist by itself as a sodium element. And helium, for example, it does exist by itself. But many other elements, including oxygen, carbon, and hydrogen, they tend to make compounds. Okay, they tend to make compounds because of their because of their activity, and also because of reasons that we are going to discuss in chapter 3 and 4. So only the noble gases, as a matter of fact, exist in nature as single atoms, and they're called monoatomic. So everything in group 8, including helium, krypton, neon, argon, they exist by themselves. Okay, but most matter is composed of molecules, or basically ions. So here we define the word molecule is a substance that is made of 2 or more atoms in a definite arrangement held together by chemical bonds or chemical forces. An example of compounds would be hydrogen molecule, H2O molecule, which is water, ammonia, which is NH3, and methane. CH4 is methane, which is a basic component of natural gas, which Qatar is rich of. So these are molecules, and they are composed of atoms. They might be the same atoms or different atoms, and they are held by chemical bonds or chemical forces. There are 2 types of molecules. There's a diatomic molecule and there's a polyatomic molecule. A diatomic molecule, it's composed only of 2 atoms, and it could be either homogeneous or heterogeneous. In other words, it could be a homonuclear atom. Homonuclear means it's made of the same types of atoms, like hydrogen, H2, N2, O2, Br2, or Cl2. These are homonuclear diatomic molecules. Or could be heteronuclear. That means it's made of 2 atoms, but they are different, like HCl. It's two different elements. Or carbon monoxide, CO. A polyatomic molecule is a molecule that is made of more than 3 atoms. An example of ozone, O3, water, ammonia, and methane. They are all polyatomic molecules. There is also something called ions, and you might know what is ions. Ions are species that have been lost or gained some electrons. Okay, so for example, sodium has 11 electrons on it. It can lose 1 electron to form a sodium ion, where this electron might go or transfer to chlorine atom. It has 17 electrons, and a Cl atom can get this electron, it becomes 18 electrons and becomes Cl minus. Whenever whenever an atom loses an electron, it becomes positive. Okay? When an atom gains an electron, it becomes negative. And that's the definition of atoms. Again, it's the same idea here that ions themselves are distributed, or they are classified as monoatomic or polyatomic. A monoatomic ion is an ion that contains only one atom. So sodium plus, Cl minus, Ca2 plus, etc. A polyatomic ions contain more than one atom. For example, hydroxide ion, OH minus, or Cn minus, or NH4 plus, or NO3 minus. These are all polyatomic ions. A positive ion is named cation. A negative ion is called anion, okay? So here, so therefore it has 11 electrons, 11 protons, because the number of protons and the number of electrons are the same in a neutral atom. And if you do the math, 23 minus 11, that would be 12 neutrons. Sodium can lose this electron, okay, to make an ion that is called Na+. And Na+, now we have only 10 electrons. The protons are not touched. We still have 11 protons, okay? And we have the 12 neutrons. So now we have a difference between the number of protons and the number of electrons. Now we have more protons than electrons does, and that's why we give the symbol of plus, Na+. Na+ is called sodium ion, or another way, cation. A cation is a general name for a positive ion. That electron that has been lost from sodium, it can go actually to fluorine. Fluorine is a non-metal. It likes to gain electrons, okay? And if you think about fluorine has an atomic number of 9. That means it has 9 electrons, 9 protons, and 19 minus 9 is 10 neutrons. That electron that has been given away by the sodium can go to fluorine, and that would be forming fluorine minus, F minus, that's called fluoride ion, okay, fluoride ion. The general name for a negative ion is called anion. So anion could be not only fluoride ion, any negative ion is called anion. How many electrons are in F minus? There are 10, because originally there were 9. Now we're adding 1 electron, so now we have 10 electrons. The protons are not touched. We still have 9 protons, and we have 10 neutrons. So now you can tell that the number of electrons here are exceeding the number of protons, and that's why the negative sign, okay? So one important thing here, that when you do chemistry, we don't play with the number of protons and neutrons, okay? This is, if you never play with the protons and neutrons, because if you do that, that's nuclear chemistry. That's breaking inside the nucleus and start playing with and that's a difficult job. That requires a lot of energy, and that happens only in nuclear reactions or in astrophysical systems like the sun, for example. But in our chemistry here, in Chemistry 101, we only can play with the number of electrons. So basically chemistry is only transfer of electrons from one atom to another. So that's the idea of ions and cations and anions. Now here's another multiple choice questions. Say species Hg2 plus is an example of what? Is it a monoatomic cation? Is it a polyatomic cation? Is it a monoatomic anion? Is it a polyatomic anion or a polyatomic metal? Again, you can think about this between you and yourself, and we can check the answer again, discuss the answer with ourselves later on. Now, common ions shown in the periodic table. This is a very important table that I want to show you here, and I want you actually to keep this table in mind for the rest of this course. In this table, this is a template of the periodic table. And I'm just going to take the first few elements here. You know, this element is hydrogen. This element is helium. Here we have lithium. We have beryllium. We have boron, carbon, nitrogen, oxygen, fluorine, and under helium we have neon and so on. And you know, the carbon has silicon underneath it, the nitrogen has phosphorus. You don't have to memorize this, but as you go with practice, you might know at least the second period by heart because of the familiarity of the first few elements. There is the halogens, fluorine, chlorine, and then bromine, and so on, and iodine. Now, this group, the first group is group 1, okay? This group is group 2, and this group is group 3, boron, 4, 5, 6, 7, 8. Okay? This is the transition metals here, which they are in the middle, and they have different group numbers, and we don't worry about them for now. So now the main group elements, the group 1, 2, 3, 4, 5, 6, all the way to 8. You will learn that the number of valence electrons, which are the electrons in the valence shell, in group 1, they are all 1. So there is 1 electron for hydrogen, 1 electron for lithium. Sodium has also 1 electron in the outer shell. They have different atomic numbers, but they are shared with the idea that they have 1 electron in the outer shell. Group 2, they have 2. Same thing for group 3, they have 3, 4, 5, 6, 7, 8. So halogens, for example, fluorine, chlorine, bromine, and iodine, they all have 7 electrons in the outer shells. Okay? So the common ions for group 1, because of the fact that they have 1 electron in their outer shell, they like to lose it, and they become noble gases, and that's why they form +1 ions. Group 2, they make +2 ions. Group 3, they make +3. Okay? And group 4, they make +4. Group 5, they have 5 electrons. They actually like to gain electrons, so they make -3. And group 6, they have 6 electrons, so it's easier for them to gain electrons, and they make all -2. This is always -1, and these kind of 0. This rule here applies to the first and second period mainly. Okay, so fluorine, for example, in most of the cases, in 99% of the cases, it makes -1. Nitrogen, it makes -3. Carbon, it makes +4. Boron, it makes +3, and so on. Okay? So carbon, for example, makes +4, and that's why it's always have 4 bonds. So keep this in mind, okay? Now, as you go for the lower periods here, phosphorus, sulfur, bromine, you might get some different rules. So, for example, the nitrogen group can also make +3 and can also make -+5. So phosphorus, for example, can make +-5, okay? Carbon can also, carbon and silicon and the bottom ones, they can make +4 or -4. Oxygen actually can make -2, -1, or -0.5, okay? That's only the exceptions in my head. As you go below in the periodic table, as you move further in the periodic table, you might have more discrepancies, and the heavy elements, they tend to make different ions. But I want you to keep this in mind. The group 1 makes +1, group 2 makes +2, group 3 +3, carbon is +-4, nitrogen is +-3, oxygen is -2 most of the cases, and halogens is -1. For the transition elements, which is the one that we did not speak about, these guys here. Now, the number of valence electrons in transition elements, they vary, okay? And therefore, the ions, they vary a lot. So, for example, chromium is an element that is known to make many ions, makes +3, +4, +5. And that's why they call it transition metals, because they transmit in their ion numbers. So nickels, for example, we have different nickels, coppers, and so on. So this, whatever we said about the rules, they do not apply to the transition metals. Now, moving on to something called chemical formulas. We talked about molecules, and now we represent molecule by a chemical formula. There are two types of molecular formulas. There's something called molecular formula, and there's something called empirical formula. Now, sometimes the molecular formula is the same as the empirical. For example, water has a chemical formula or a molecular formula of H2O. It's the same as empirical formula. I'm going to show you what I mean in a few seconds. Now, molecular formula shows the exact number of atoms of each element in the smallest unit of a substance, while an empirical formula shows the simplest whole number ratio of the atoms in a substance. Empirical formulas are determined experimentally. So an example of that would be, so let's take a few examples for determining the molecular formula and the empirical formula. Let's take water. Let's take H2O2, which is hydrogen peroxide. Let's take CH4. Let's take CH3, which is ethane. Okay? And let's take one more, which is let's take one more, which is N2O4, dinitrogen tetroxide. Now, this is called the molecular formula. This is called the molecular formula. Now, what is the empirical formula? The empirical formula, you obtain it by thinking about the simplest way in whole numbers to write these. To write H2O, for example. H2O is H2O, so can I divide this by 2? It's HO half. No, that's not going to work. So the empirical formula for H2 is the same. Now for H2O2, if I divide this by 2, it's going to be HO or OH. So that's possible. So in this case, we say that the empirical formula for hydrogen peroxide, which is H2O2, is OH. CH4, can I divide by something to get a simpler way of this? CH4, I cannot, because C has 1. So if I divide by 2 or 3, that's going to give me fractions. That's not going to work. So empirical formula for methane is the same as CH4. CH3, which can be written also as C2H6. This can be simplified into CH3. Okay, so that's the empirical formula for ethane. N2O4, indeed, it can be simplified in NO2 if we divide by 2. Now, I want to say something that is important. First of all, the empirical formula might not be representing a true compound. So, for example, OH. There is no compound called OH. There might be something called hydroxide and ion, which is OH minus, which is a different story. CH3 is not a true compound. There is something called CH3 radical, which you will study in organic chemistry. But that's not a true compound. Okay, so empirical formula might not be itself a true compound. The other thing is an empirical formula might represent more than one compound. Take this, for example, NO2. NO2 is the empirical formula for this. It's actually also the empirical formula for a gas called NO2. There is a gas called nitrogen dioxide. So the empirical formula for both these gases, this gas and this gas, okay, is NO2. CH3, for example, is another example of an empirical formula that can be an empirical formula for this compound, which is ethane, and it could be also an empirical formula for something else, if you want to think about it. Okay. So here are some examples in this slide of how to write the empirical formula for some compounds. And this slide shows you different ways of representing molecules. First of all, let's take water, for example. The molecular formula of water is H2O. If you write the structural formula, that would be an oxygen, and there is 2 hydrogen to each side. It's connected by chemical bonds. There is the ball and stick model, which is the one that is widely used in chemical textbooks, in chemistry textbooks, showing you the connections of these balls and the bonds. And there is also the space filling model that gives you a more realistic vision of the molecule itself. The first 3 are the most common used in chemistry textbooks. This example asks you, write the molecular formula of methylamine, which is a colorless gas used in the production of pharmaceuticals and pesticides, from its ball and stick model shown in the margin. So here you have a picture of a molecule called methylamine, and you're asked to write down the molecular formula. Molecular formula. If you see this table again, the molecular formula would be the first row here. So we need to write this as a molecular formula. If you count how many elements we have 1 nitrogen, we have 1 carbon. The carbon is attached to 3 hydrogens, and the nitrogen is attached to 2 hydrogens. So you might start thinking about different ways of doing this. And so you have carbon attached to 3 hydrogens, and you have nitrogen here attached also to 2 hydrogens. So you can write this as CH3 and then NH2. That would be the correct one. Some people, they like to write NH2 and then CH3. There are, of course, you can write H3, C, and then N, and then H2. There are different ways of writing this, but usually we arrange the elements as shown in the periodic table, so carbon first, and then nitrogen. Also, this shows you that there are 3 hydrogens connected to carbon, 2 hydrogens connected to nitrogen, so that would be the correct formula, okay? That's not very incorrect, but there are some rules to write organic molecules, and that would be the most correct one. In this question, it says, write the empirical formula for the following molecules. Diborane, B2H6, used in rocket propellants. So B2H6, if you think about dividing by a number to get a simpler formula, yes, we can do that. We can divide by 2 and get BH3. BH3, okay? So that's empirical formula for B2H6. Dimethyl formaldehyde, C8H12O4. Yeah, we can do that. We can basically divide by 4. That will give you C2H3O. So C2H3O, that would be the empirical formula for this one. And I can also think about number C. Okay, so that would be the end of my lecture for today for chapter 2. Inshallah, next time we're gonna continue with chapter 2, and then we'll solve more problems. Thank you so much for attending this lecture, and have